A strong biostatistics project starts by translating a real-world question into a question that data can answer. Real-world questions are often broad, like, is this program working? Or is this treatment better? A statistical version of that question has to be specific about who, what is being compared, what outcome, and what time frame. For example, is this program working becomes something like, among eligible participants, what is the difference in completion rate within 90 days between those offered the program and those not offered the program? Another example, is this treatment better? Becomes, among adults with condition X, what is the difference in average symptom score after 8 weeks between treatment A and treatment B? That translation matters because a broad question can produce vague results, while a specific question produces an estimate you can interpret and act on. A useful way to structure this translation is with PICO or PACO. PICO stands for Population, Intervention, Comparator, Outcome, and is commonly used when there is intervention. PICO stands for Population, Exposure, Comparator, Outcome, and is commonly used when studying an exposure rather than an assigned intervention. This structure forces clarity. For example, population might be pregnant people receiving prenatal care in a specific system. Intervention might be a text message reminder. Comparator might be no reminders, and outcome might be attendance at a recommended visit within a time window. Another example, outside healthcare. Population might be new employees. Exposure might be completing onboarding within 2 weeks. Comparator might be not completing onboarding within 2 weeks, and outcome might be retention at 6 months. In education, population might be students enrolled in Algebra 1, intervention might be tutoring, comparator might be no tutoring, and outcome might be pass rate on the end of course exam. Framing also means choosing the type of outcome because the outcome type drives how you analyze it. If the outcome is a binary outcome, yes, no, like completed program or had a hospitalization, the statistical question is often about comparing proportions or risks. If the outcome is continuous, a numeric scale, like blood pressure, score, or wait time, the statistical question is often about comparing averages or medians. If the outcome is a count, like number of visits or number of defects, the question is often about comparing rates. If the outcome is time to event, like time until relapse or time until readmission, then the question becomes, how quickly does the event occur and needs survival analysis ideas? For example, do reminders improve follow-up can mean higher follow-up rate within 6 weeks, binary, or shorter time to follow-up, time to event. Both are reasonable, but they answer slightly different questions, so choosing one is part of framing. Framing also requires deciding what better means in a way that is measurable and fair. Better could mean fewer adverse outcomes, improved quality of life scores, fewer missed appointments, lower cost, or a balance of benefits and harms. For example, a new screening approach might increase detection, a benefit, but also increase false positives, a harm. So the statistical question may need multiple outcomes: detection rate, false positive rate, and downstream follow-up burden. Another example, a workflow change might reduce wait times but increase staff overtime. A full statistical framing might compare both wait time and overtime, rather than declaring success from only one metric. In safety or operations, a process change might reduce the average number of errors but increase variability. The statistical question might need both average level and variability to reflect the real impact. Finally, framing should specify what the comparison represents. Is it a comparison of groups, treatment A vs treatment B? A comparison over time, before vs after a policy change? Or a comparison of dose intensity, more exposure versus less exposure? Each implies different pitfalls. For example, before-after comparisons can be distorted by seasonality or unrelated changes happening at the same time. Group comparisons can be distorted when groups differ in baseline characteristics, confounding. Dose comparisons can be distorted if people receiving more intensity are systematically different. For example, higher need individuals get more services. Good framing does not solve these problems by itself, but it makes them visible early, so the study design and analysis can address them honestly. A key step in biostatistics is deciding what the primary endpoint is. An endpoint is the outcome you measure to judge whether something worked or changed. The primary endpoint is the main outcome the study is designed to answer, and it is the one that gets the most weight in the final conclusion. This matters because a project can produce dozens of possible outcomes, but only one or a small number should be treated as the main target. For example, if you are evaluating a new treatment, the primary endpoint might be symptom improvement at 8 weeks, while other measures like lab values or side effects are important, but not the main decision point. In a program evaluation, the primary endpoint might be completion within 90 days, even though satisfaction and engagement are also tracked. In operations, the primary endpoint might be average time from request to service, even though rework rate and cost are also relevant. Secondary endpoints are outcomes that add context, explain mechanisms, capture trade-offs, or address broader stakeholder needs. They are important, but they are not the single main pass-fail yardstick. Secondary endpoints often include safety outcomes, quality outcomes, utilization outcomes, and subgroup outcomes. For example, if the primary endpoint is reduced hospitalizations, secondary endpoints might include emergency visits, medication adherence, and adverse events, side effects. If the primary endpoint is improved test scores, secondary endpoints might include attendance, course completion, and student satisfaction. If the primary endpoint is reduced defects, secondary endpoints might include production speed, worker injuries, and customer complaints. Secondary endpoints are how you prevent a narrow view of success because real-world decisions rarely depend on one number alone. Separating primary from secondary endpoints is also a protection against finding something that looks good by chance. When many endpoints are tested, some will appear improved even if nothing truly changed, simply due to randomness. This is called the multiple comparisons problem, also called multiplicity. A typical approach is to pre-specify one primary endpoint and treat the rest as supportive, exploratory, or controlled with additional methods. For example, if you test 20 outcomes and use a typical 5% significance threshold, you should expect about one outcome to look significant just by chance, even when there is no real effect. In a business setting, if you compare 30 sites across 12 months, some will look unusually high or low just from normal variation. In health research, if you examine many side effects, some may appear associated with a treatment by chance unless there is a plan for how to interpret that long list. There are practical strategies to handle endpoints responsibly. One approach is a hierarchy, sometimes called gatekeeping, where you test the primary endpoint first, and only if that is convincing do you formally test key secondary endpoints in a planned order. Another approach is adjusting for multiple comparisons using methods like Bonferroni correction, a conservative way to lower the threshold when many tests are run, or controlling the false discovery rate, a way to limit the expected proportion of false positives among the results you call significant. A third approach is to label some outcomes as clearly exploratory and use them to generate hypotheses rather than to claim proof. For example, a project might have one primary endpoint, two key secondary endpoints with a planned testing sequence, and then several exploratory outcomes used for learning and future planning. Endpoint definition must be specific enough that two different analysts would measure it the same way. This means specifying the time window, the measurement method, and how edge cases are handled. For example, readmission should specify whether it is within 30 days, whether it counts planned readmissions, and what happens if someone goes to a different facility. Program completion should specify whether partial completion counts, whether completion requires all modules, and whether there is a grace period. Defect rate should specify defects per item, per batch, or per inspection hour, and whether repeat inspections are counted. Even blood pressure improvement should specify whether it uses the last measurement, an average of multiple measurements, and whether the measurement is standardized. Endpoint precision is what keeps results interpretable and comparable. Finally, endpoints should reflect what matters and avoid being convenient but misleading. Sometimes a highly available metric is not the best representation of impact. For example, a program might improve appointment attendance, easy to measure, but not improve the health outcome the the program was meant to influence, harder to measure. A workflow change might reduce average wait time, but increase the percentage of people who abandon the process, a harm that average wait time can hide. A screening change might increase the number of positive results, but if the positives are largely false positives, the benefit is not real. Strong endpoint planning aims for outcomes that are meaningful, measurable, and aligned to the decision, while also including secondary endpoints that capture trade-offs and unintended consequences. An estimand is the exact thing you are trying to estimate with data. It is a way to remove ambiguity so that the analysis and the interpretation line up perfectly. Many projects fail because people think they're answering one question, but their data and methods actually answer a slightly different one. The estimand idea forces clarity about what the effect even means. For example, does this intervention improve outcomes? Can hide several different meanings. Improve outcomes among everyone who was offered it, among only those who actually used it, or among those who used it exactly as intended. Another example, does exposure X increase risk? Can mean risk over 30 days, over 1 year, or over a lifetime, and it can mean risk for the full population or only for a subgroup. Estimands make those choices explicit so results are not misunderstood. The first part of an estimand is the population. This is who the result is meant to describe. The population be all eligible people, people who actually participated, people with complete follow-up data, or people meeting strict inclusion criteria. Each choice changes what the estimate means. For example, if the population is all eligible people, then the estimate answers a real-world question about what happens if the program is offered broadly, including people who never fully engage. If the population is people who participated, the estimate describes something closer to what happens among engaged participants, which can look more favorable but may not reflect real-world rollout. Another example, if your population is defined as people who have a certain lab test on record, you may unintentionally exclude people with limited access or incomplete records, which changes who the results apply to. Being explicit about population helps avoid claims that go beyond what the data truly represent. The second part is the treatment condition or exposure condition and the comparison condition. This is what is being compared, and it must be described in a concrete way. In randomized studies, the comparison might be assigned to intervention A versus assigned to intervention B. In non-randomized settings, the comparison might be received the new workflow versus received the old workflow, or high exposure versus low exposure. The key is to define it clearly enough that the comparison could be reproduced. For example, received follow-up support should specify what counts as receiving it, number of contacts, time window, minimum dose. Another example, policy implemented should specify the implementation date, what sites were affected, and whether there was a ramp-up period. Without this clarity, two analysts can produce two different estimates while believing they are measuring the same thing. The third part is the outcome and how it is measured. This includes the definition, time frame, and any rules for handling common edge cases. For example, an outcome like improvement should specify how much improvement counts and how it is measured. Change from baseline, final value, or percent change. For outcomes like readmission, it should specify the time window and what counts as the event. For outcomes like completion, it should specify what activities are required and whether partial completion counts. The time frame is especially important because a short window can miss delayed benefits, while a long window can blend together many influences. For example, a short-term outcome might show rapid improvement, while a longer-term outcome might show the effect fades. Another example is the reverse. A short window might show little difference, while benefits appear later. The fourth part is the summary measure, meaning how the effect will be expressed. This is the number you plan to estimate, a difference, a ratio, a rate, a time difference, or something else. For example, for a yes-no outcome, you might use risk difference, absolute difference in probability, risk ratio, relative difference in probability, or odds ratio, a ratio using odds rather than probability. For a continuous outcome like blood pressure or wait time, you might use a difference in means or a difference in medians. For count outcomes like number of events, you might use an incidence rate ratio, which compares event rates accounting for different amounts of time observed. For time to event outcomes, you might use a hazard ratio, a comparison of event rates over time, or a difference in survival probabilities at a specific time point. Different measures can tell different stories, so choosing the measure is part of defining the estimand, not an afterthought. Estimands also clarify how to think about real-world complications such as non-adherence, switching, and missing outcomes. For example, one estimand might answer, what is the effect of being assigned to the intervention, which reflects real-world rollout, including partial uptake? Another estimand might answer, what is the effect among those who actually received the full intervention, which can be useful for understanding the maximum potential, but is harder to estimate fairly because the people who adhere may differ from those who do not. In plain language, one estimand is about the effect of offering or assigning, and another is about the effect of actually taking or completing. In many settings, both are valuable, but they answer different questions and should not be mixed. Finally, estimands help keep communication honest because they create a direct bridge from question to result. If the estimand is clear, then it becomes easier to explain what the analysis did and what it did not do. For example, if the estimand targets the full eligible population, then the results are naturally appropriate for planning and policy decisions about broad implementation. If the estimand targets only engaged participants, then the results are better framed as what is achievable under strong participation, not what will automatically happen for everyone. If the estimand uses a 90-day outcome window, then it should not be used to make claims about year-long impact. Estimands are the guardrails that prevent overreach and keep a project aligned from the first question to the final decision. A hypothesis is a clear statement of what you are testing or estimating, written in a way that connects directly to the data. It usually comes in two parts, the null hypothesis and the alternative hypothesis. The null hypothesis is the no difference or no effect baseline that you test against. The alternative hypothesis is what you would conclude if the data provide enough evidence against the null. For example, if comparing two approaches, the null might be that the average outcome is the same in both groups, and the alternative might be that the averages differ. If comparing two rates, the null might be that the rates are equal, and the alternative might be that one rate is higher or lower. Even when a project is more focused on estimation than on testing, hypotheses still help clarify the direction and the decision rule. Directional versus non-directional hypotheses describe whether you are testing for change in one specific direction or in either direction. A non-directional hypothesis is also called two-sided, meaning the alternative allows for either an increase or a decrease. This is common when you want to detect any difference, regardless of direction, or when you want to avoid assuming the direction ahead of time. For example, if evaluating a new workflow, it could plausibly improve outcomes or accidentally worsen them. So a two-sided approach makes sense. Another example, if comparing two treatments with uncertain trade-offs, one could be better or worse, and two-sided testing reflects that uncertainty. A directional hypothesis is also called one-sided, meaning the alternative focuses only on one direction, such as the new approach is better or the new approach is not worse. Directional hypotheses can be appropriate when only one direction is meaningful for action and the opposite direction is not a plausible claim you would accept, but they require discipline because they can be misused to make results look stronger than they are. Superiority versus non-inferiority is another major framing choice that changes the hypothesis and the interpretation. A superiority question asks whether one approach is better than another by some amount, with the null typically being that there is no difference. For example, superiority might mean a new treatment improves symptom score more than standard treatment, or a new program increases completion rates compared with the current program. In contrast, a non-inferiority question asks whether a new approach is not unacceptably worse than the standard by more than a preset margin. This is used when the new approach may have other advantages like lower cost, fewer side effects, easier delivery, or broader reach, and you want to show it is close enough on the main outcome. For example, a shorter training program might be acceptable if outcomes are not worse by more than a small margin because it saves time and money. Another example, a more convenient medication schedule might be acceptable if effectiveness is not meaningfully worse because adherence could be better in real life. The non-inferiority margin is the centerpiece of non-inferiority hypotheses, and it must be chosen thoughtfully. The margin is the largest difference that would still be considered acceptable, and it should be based on practical or clinical reasoning, not selected to guarantee a favorable outcome. For example, if the standard approach yields a 70% success rate, stakeholders might decide that a new approach is acceptable if the success rate is no more than 5 percentage points lower, because the new approach dramatically improves access. Another example, for a continuous outcome like a score, stakeholders might decide that a difference of 2 points is the largest acceptable loss because anything larger would be noticeable and important. The key is that the margin should be defined before analysis and justified in a way that can be explained clearly. Without a justified margin, non-inferiority becomes a label rather than a defensible conclusion. Directional choices and superiority, non-inferiority choices all affect how uncertainty is used. In practice, these questions rely heavily on confidence intervals, which are ranges of plausible values for the effect. For superiority, the confidence interval should show that the effect is above 0 in the favorable direction if you want to claim improvement. For non-inferiority, the confidence interval should stay above the negative margin, not crossing into too much worse, if you want to claim the new approach is not unacceptably worse. This is important because it shifts attention away from a single p-value and toward the whole range of plausible effects. For example, a result might have an average difference that looks small, but if the confidence interval includes meaningful harm, then claiming non-inferiority would not be responsible. Another example, a result might be favorable on average, but if the uncertainty is wide, it may not support a strong superiority claim. Finally, hypothesis framing should match what decisions will actually be made. If a decision requires evidence that something is better, superiority framing aligns with that. If a decision is about adopting something easier or cheaper, as long as it is not meaningfully worse, non-inferiority framing aligns with that. Directional hypotheses should be chosen based on the real decision logic, not to get a smaller p-value. Clear hypothesis framing also helps prevent post hoc storytelling, where the hypothesis is adjusted after seeing results. For example, if a project was planned as superiority but results are not strong, it is not appropriate to relabel the goal as non-inferiority unless that was truly the original decision context and the margin was defined in advance. The hypothesis is not just a technical step. It is a contract between the question, the analysis, and the interpretation. Alignment means the research question, the study design, and the analysis plan all point to the same target. When they do not align, the project can produce a technically correct analysis that answers the wrong question. A good way to think about alignment is that the research question defines what you want to know, the design determines what information you can credibly learn, and the analysis plan translates that into specific statistical steps. For example, if the question is, does this cause improvement? A design with random assignments supports that type of claim much better than a simple before and after comparison. Another example, if the question is, how quickly does an event happen? The design needs time to event information and follow-up time, and the analysis plan needs survival methods rather than a simple comparison of proportions. Design is the foundation because it determines what comparisons are valid and what biases are likely. If the design creates comparable groups, the analysis has a simpler job. If the design creates groups that differ in important ways, the analysis must work harder to address confounding and may still be limited. For example, if two groups differ greatly in age, baseline severity, or access to care, then a simple difference in outcomes is not a fair estimate of the effect of the exposure or intervention. Another example, if a program is offered only in certain locations and those locations have different resources, staffing, or population characteristics, the design has built-in differences that must be accounted for. In time-based designs, if an intervention starts at the same time as other major changes, it becomes difficult to isolate which change caused what. Good alignment anticipates these issues early rather than discovering them after the fact. The analysis plan is where the alignment becomes concrete and operational. This includes definitions, inclusion and exclusion rules, how variables are coded, what models or tests will be used, and how results will be presented. For example, if the question focuses on a binary outcome, the plan should specify whether the main measure will be risk difference, risk ratio, or odds ratio, and why that choice is appropriate. If the question focuses on comparing rates across groups with different exposure times, the plan should specify a rate-based approach, such as Poisson regression with an offset. If the question focuses on time until an event, the plan should specify survival analysis methods and how censoring will be handled. The plan also should specify which comparisons are primary versus secondary, so that the main conclusion is not driven by whichever analysis looks best after exploring multiple angles. Alignment also requires matching the unit of analysis to the decision context. Many settings involve data with multiple records per person, multiple people per site, or repeated measures over time. If the research question is about individuals, but the data are clustered within sites, the analysis must reflect that clustering or it can overstate precision. For example, if people are nested within clinics or schools, outcomes may be correlated within those clusters, and treating each observation as fully independent can make confidence intervals too narrow. Another example, if each person contributes multiple visits, then counting each visit as a separate person inflates sample size and can distort conclusions about how many people are affected. Aligning unit design and analysis prevents errors that look subtle but can completely change the credibility of results. Real-world alignment also means planning for practical issues like missing data, measurement differences, and implementation variability. A perfectly designed analysis can still fail if key outcomes are missing in a biased way or measured inconsistently. For example, if follow-up data are more often missing for people with worse outcomes, a naive, complete case analysis can make results look better than they are. Another example, if different sites implement an intervention differently, the analysis plan should consider whether to estimate an overall average effect, site-specific effects, or an effect that accounts for varying intensity. Alignment here means the plan anticipates what the data will actually look like and includes steps to check assumptions, describe missingness, and test whether results are sensitive to reasonable alternative choices. Finally, alignment shows up in the final interpretation and communication. If the design is observational, aligned communication avoids claiming certainty about causation and instead describes associations with appropriate caution and context. If the design supports causal inference, aligned communication still includes uncertainty and acknowledges limitations. For example, an aligned report will clearly state what population the results apply to, what time frame was studied, what outcome definition was used, and what comparisons were made. Another example, if multiple outcomes were examined, an aligned report will highlight the primary endpoint as the main conclusion and frame secondary endpoints as supportive or exploratory. Alignment is what turns biostatistics from running analyses into an evidence process that is coherent, defensible, and useful across different jobs and settings.